All right. How to identify the torque is the neutral axis after deformation remains at the same location. Okay, so that's how you identify it, because later on we're going to do a lot of bending moment and torque, and you're like, is this a moment or a torque? Okay, once you get this wrong, okay, unfortunately, your answers will be wrong. Okay, so some of you, Eugene is fine. I can get my answers wrong, and I can put a factor of safety, right? So what is the short form of factor of safety? Anyone? What do we call factor of safety? Anyone, please? FOS, right? Factor of safety, right? So if you do the wrong factor of safety, right? If you put it too big, it's not good news, is it? Okay. So anyway, so now torque is in the x-axis. So we have FOS. You have, I'll make you laugh, okay? So 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 FOS is factor of safety. If you know what you're doing, right? The factor of safety in depending on the application can be 1.3 to 1.5. Okay. If it is dynamic loading, okay, you usually put a bit more. But if you put a factor of safety of 10, what does it mean? Anyone? Anyone, please? If you put a safety factor of 10, what does it mean?
You have no idea if you're right or not.
Yeah, means your analysis is full of shit. Yes or no? Okay, FOS, right? Okay, so you have to have that confidence. I've seen engineers in practice. The value is too small. I'm going to touch a 1.5. Okay, don't do that. Don't do that. Okay. So this is equal to 2,000 pound inch, right? And it's rotating in this direction, right? So once you have this, right, you know that what formula that you're going to apply is shear stress is equal to TR over J. Okay, so you're going to apply this, and if we were to consider element H and element K, right, and we realize that both element H and element K will give us tau max, because the radius over here for element H and K will be R max. Okay, so R will be R max. So like what we drew before in terms of shear stress, right? So this is our shear, this is our radius. We tend to have this sort of linear relationship. Okay, so that is our now all this is relative to R, yeah, radius. Okay, so that's how we identify our shearing stress, okay, induced by the torque. Okay, so now I'm not combined all of them yet. Okay, later on we're still identifying what's a moment, what's a shearing force, and what's a torque. Later on, when we start constructing an element, we have to combine all the loads together. Okay, so now not yet. Okay, now so this is one example. Let's look at another example. I want you all to be very comfortable on identifying your moments and your torque. So let's pick another example. As I mentioned earlier, I've uploaded all these images on Avenue to Learn. So don't copy them, just go to Avenue and have a look at them. Okay. Right. So this is example number 2. Okay, this is example number 2. Anyone has question, please? Anyone?
No, so we didn't solve any stresses in the last question. We just solved for the forces.
Yeah, deliberately. deliberately because I'm at this stage. I'm
Oh,
just
okay. We're just getting
identifying the bending. I want you all to be very sure to calculate what is a bending moment, shear force, and a torque. Don't worry, okay? More trouble will come your way, okay?
Alright.
Okay, so now we look at this structure now, okay? So the first thing we're going to do is identify which is our X, this is our Y, and this is the Z, okay? And again, we have to focus on where is the point of interest. I repeat again, we have to focus on where the point of interest is. So now we are very interested in what is going on element H. Okay, what is it going? So once we know what we are trying to identify, immediately construct your what? Neutral axis. Okay, so I'm going to construct our neutral axis now. Okay, so this is our neutral axis. This is just a sketch, okay? So this is our neutral axis. Okay, so now not necessary all neutral axes are horizontal. Okay, so for this case, it's a classical problem that I want you to see for yourself that the neutral axis can be in the vertical side. Okay, so now there are two forces that we have to find. Okay, there are two forces. Okay, so the force over here, the 13 kilonewton is acting on the YZ plane. Yes, you can see. So one force will be coming down here. Then you have another force coming this way. Okay, so the force that's coming down vertically, that is our Fy. Running on the horizontal, that is our Fz. Or not call. I'm going to call based on the location dy. This is our dz. Okay, so we're going to find what is our dy and what is our dz first. Okay, so dy. Okay, so we're going to find our dy, right? So to find our dy, so so it's equal to dy over 300, and this is equal to 13 times 10 to the power 3 divided by 300 squared plus by 125 squared. Okay, so I'm using similar triangles. So this will be equal to 300 divided by square root of 300 squared plus by 125 squared, the whole thing square root. Okay. Hold on, I'm lost with my calculator. Okay. Okay, so equal. No. I got it. So it's square root of 300 squared plus by 125 squared, close bracket. Okay. So equal to 300 divided by the square root times by 13 power 3. So it's equal to 12,000. I mean, you can use sine and cosine. You get the same thing. I did not use the sine and cosine because it reduce the rounding. Okay. Then we're gonna find dz. Right. So dz over, if I look at dz, is over 125. So this is equal to 13 times 10 to the power 3 divided by squared plus by 125. So dz is equal to 125 times 13 power 3 divided by square root bracket 300 squared plus 125 squared close bracket. So it's equal to 5,000. Okay. Yeah, I get 5,000. Wait, 300 squared plus by 125 squared. Okay. Square root of the whole thing is 325. Yep. 13 power 3 divided by this times by 125. Yep. Okay. So this is 5 times 10 to the power 3 Newton. Okay. So that is our That is our forces. Okay, 12 squared. Hold on, let me check something. Yep, it's correct. So now we have all those. Okay, so same thing. Okay, so we call this. Okay, so I'm going to draw X. Then we have Y. Then this is rotation about Z. Okay, so I'm going to construct the view in the XY plane. Okay, the view on the XY plane. So from here, okay, so it's 300. So I'm going to sketch this out. So it's 150. Okay, and then the vertical. So if you look at the vertical, we are going to do just 200. Okay, I'll tell you why just 200. Because where the element is, okay, where the element is standing is at 200. Okay, so from here, first thing we're going to do, we're going to construct the neutral axis. Okay, and then this will be our, so down here, exactly down here, that is our element H. Okay, that's our element H. So by constructing this view, we know that we have two forces. Okay, so one force will be at so that will be our dy. So dy is 12 times 10 to the power 3. And then our dz, which is going away, is 5 times 10 to the power 3. Okay, 5 times 10 to the power 3. Okay, so let's see what we have. Okay, so based on Newton's third law, right, the 12,000 has to be transmitted into here. Right, not Newton's third law. You just push the load onto the neutral axis, and the reason I've explained why. Okay, so if you look at yesterday's notes, okay, so this is yesterday's notes, right? It's for this reason. Where is it? Right, it's for this reason, right? Remember I taught you about this, right? We explained. Okay, we explained what is going on down there. Okay, sorry, this diagram over here. Okay, so I've explained why we have to put the P or the axial load, okay, into the neutral axis. Then from here, okay, so we now know. So let's write in our first load. So our P in Y, right? Our P in Y is going to generate 10, 12 times 10 to the power 3 Newton, and on element H, is going to construct. It's going to have a compression. Right, is a compression. And the form, if you want to write the formula, so stress X is equal to Py divided by area. So the area we're going to consider is the area where element H is located, right? So don't get confused, okay? Then the next one is this, right? The next one is over here. We have distance, right? So we know, yes, someone has a question.
Oh, sorry to interrupt, but why did you write 12 times 10 to the third newtons twice in two different spots?
Oh, it's not different. Sorry, the 12,000 over here will transmit an axial load of 12,000 on the neutral axis.
Oh, okay, my bad.
And the reason why was I explained yesterday, right? Okay.
Okay.
Right.
Thanks.
You're more than welcome. Okay. Hey, I like that. Okay. What you don't understand, ask now. Okay. Don't try to like really figure out. Then you have no idea. Then get frustrated. Okay. Ask. I like that. Okay. So now it comes to the 12,000. Right now it comes to the 12,000. So the 12,000 is going to generate a moment. Okay. So we know there is that moment is equal to force times by perpendicular distance. Right? But what is this perpendicular distance?